So hopefully you have been in lessons this week and you will have seen the proof of the derivative of e to the power of x and the ln x from first principles. And so we know that dy by dx in this case, I've got a very thick pen here, let's go down the sides, okay, is itself, it's part of the definition of e to the x, and the derivative of ln x is 1 over x. Today we're going to use some of those, or rather those two rules, in some questions. So instead of e to the x here, I've got e to the power of 3x squared plus 7. Now, I know how to differentiate e to the x. I know how to differentiate 3x squared plus 7. So I must have a chain rule problem here because one of these functions is tucked inside the other one. It's in place of something I would know how to differentiate. So let's set up a chain rule problem. So we'll say, well, y is e to the t, where t is 3x squared plus 7. Don't forget to keep your layout really, really careful. It's really important because it just stops us making mistakes. So dy by dt, the derivative of the function y with respect to t, which is our variable at the moment, is e to the t, it's part of the definition. And dt by dx is 6x. Obviously our 7 disappears. Using the chain rule, then we know that dy by dx is dy by dt multiplied to dt by dx. So that is e to the power of t multiplied to 6x. And obviously we're going to write that out a little bit nicer. That's 6x e to the power of t, which is 3x squared plus 7. And that is dy by dx. So just used that new rule that the derivative of e to the t is e to the t, or e to the x is e to the x, whatever the variable is. In the case of ln, again, if it would have been ln x, I would know how to differentiate it, that's 1 over x. But instead I've got ln of x squared plus 2x plus 1. So I've got another chain rule problem. So we'll write our chain rule out. So y equals ln t, where t is x squared plus 2x plus 1. dy by dt is equal to 1 over t. That we discovered in lessons this week, and if you weren't in lessons, you now know it. And dt by dx is 2x plus 2. Pulling these back together, then we'll use the chain rule. So we know that dy by dx is dy by dt multiplied to dt by dx. So that's 1 over t multiplied to 2x add 2, which is 2x add 2 over t, which is x squared add 2x add 1. Now there are some interesting things going on here. So we've basically got the derivative on top of the t function here, which I think that's clear from what we had previously. And in the other question, we had the derivative multiplied to the power, which was t. So we can what we've just been talking about here. So if we have a function e to the power of something, and we'll call that something f of x, then dy by dx is the derivative multiplied to the original thing. And we can prove that using f of x. So we'll say, well, y is e to the t, where t is f of x. Don't know anything about f of x, I just know that it's some function. Then dy by dt is e to the t, we know that. And dt by dx, well, we don't know what f is, so all we can do is notate it as the derivative, whatever that is. Then we know that the chain rule gets us to multiply, so we'll multiply those to find dy by dx, which is f prime of x, the derivative, multiplied to e to the t, and t is f of x. So it's just the function again, but multiplied to the derivative. And that's a really important structure to remember, because if we start to integrate and go backwards, it's a really nice thing to spot and just write down straight away. Likewise, with ln of some function, we now can see, hopefully, and we'll prove it again in a minute, that the derivative is the derivative of the inner function over the original function. And again, if we just use the chain rule to prove that, we can say, well, y is ln t, where t is f of x, some function, not sure what. dy by dt is 1 over t, and dt by dx is the derivative of whatever the function is, and we'll notate that f prime. Pulling those back together then, dy by dx is equal to f prime of x multiplied to 1 over t, which we can just write as f prime of x over t, and t is f of x. Again, a really important structure to remember, particularly for when we integrate. It's one of those first things we can check for. If you can spot the derivative of a function over that function, you know straight away it's the ln. And it's really, really useful, saves you tons of time trying to figure things out in other ways. So we've done the chain rule versions, and they are really useful for just being able to differentiate really quickly because they've got those really nice structures. But it's worth remembering that there are other types of techniques we've got for differentiation, and E and ln might appear in those as well. So here we have a product rule problem because we've got two functions, e of x, which we can denote u, and this quadratic here, which we can denote v. So if y is u times v, we can set what u is, e to the x, what v is, x squared plus 7x minus 1, and use the standard rules of the product rule to differentiate this. So we need du by dx, which is e to the x, and we need dv by dx, which is 2x add 7. Now, we know that the product rule tells us that dy by dx is u dv by dx plus v du by dx, or the other way around because it's addition there. So we could write that v du dx plus u dv dx if we'd prefer. So just substituting everything in, and hence why the layout is so important. U is e to the x, dv by dx is 2x add 7, v is x squared add 7x minus 1, and du by dx is e to the x. Now, of course, I can factorise this, and I should do because I can actually simplify this and sort this out. I'll pull the e to the x out, and that will leave me with x squared add 7x add 2x, which is add 9x, and minus 1 add 7, which is 6. Again, another product rule problem. Here's my u, but this time my v is involving ln. So just a different version, I guess. So u is x cubed minus 5, and v is ln x. Differentiate both of those. That's 3x squared, and the minus 5 disappears. And dv by dx is 1 over x. Pulling those together according to the product rule, which tells us that's u dv dx plus v du dx, gives us u, so x cubed minus 5 times by 1 over x plus ln of x times by 3x squared. We could sort this out. I don't know whether we're going to find anything that will actually help us. So multiplying this x cubed minus 5 by 1 over x will give us x squared minus 5 over x. And then we've got 3x squared ln x. There's nothing really common there. I guess I could pull out a 1 over x and increase the power on the other two terms, but I don't think there's anything obvious there, so we can leave that. Just don't forget that just as with any differentiation problem, now that you're past the point of C1, you could be asked for tangents and normals, you could be asked for stationary points, and you could be asked now to combine the chain and the product or quotient rules together. They use E and ln in these all the time, so you could have something like, I'm not even sure, let's just make something up. So x squared plus 7 e to the power of, I don't know, 2x squared plus 3. Also, it doesn't really matter, but look, there's a product there, and when we get to the v term, we'd have to also use the chain rule. There's your chain bit. So yeah, just don't forget those kind of other techniques there. Nothing different about these bits. They're exactly the same standard techniques we've been using since C2, but they could appear in these types of questions as well.